We'll finish that discussion. Then I will spend some time going over solution to homework 3. After which we're gonna carry out the quiz, okay, for quiz number 2. And with that, we cover everything you expect to know for the midterm test coming out on Thursday. Okay. The quiz, as I mentioned several times, the quiz itself is closed book. You're not supposed to refer or look at any materials. For midterm though, I'd like to mention that it is open book. But I'd like to define what I mean by open book. What I mean really is you can refer to all the homework solutions and quiz solutions and lecture slides. If you decide to bring a laptop, that's okay, but make sure you only access our website, the class website, nothing else. If I see you using Google or any other website outside the class website, then you are immediately removed from the exam. You get 0 from the midterm. Is that clear?
Can you bring your book?
You can bring textbook, yes. But only textbook.
E-book?
E-book is fine. If you have a copy of e-book, that's okay. Yes, of course. Any other question? Yes, Mark?
Database server?
No. So I don't want you to be able to connect to the server and test the SQL. Okay. Any other questions? In other words, no database server, no MySQL workbench. The only thing I should see from your laptop is a browser, potentially, and the browser stays at the class homepage. Yeah.
Did you say that the exam would be 130 minutes? Or did you say the exam was longer than last night?
Oh, the exam will be 1.5 hours. So it will be 90 minutes. I think the class is about what? Class is 25, 35.
21.
Class is 80 minutes, right? So we need 10 more minutes. So what we're gonna do is we will start 10 minutes earlier than 12:25, which means we will meet at 12:15 on Thursday. I will send out another reminder in the announcement page so that you are all aware of that. And also do spread the news to your friends. If he or she is from this class, make sure that everyone knows that you need to come 10 minutes earlier on Thursday to get ready for the midterm. Another thing that might be useful for you is to bring a calculator, or just use your calculator from your laptop. You will need that for some of the calculations when we ask you about configuration of the tree, the size, the page size, the height, the I/O cost, and all that. Okay, which actually you will see some of that from quiz number 2 today. Yeah, question over there?
At what point we have to wait for the report? Till what slide?
Huh? Until what slides?
Yeah.
Well, everything up to the end of V+3, except the dynamic insertion and deletion of V+3. I will not test that, but everything other than the dynamic insertion deletion of V+3 will be part of your midterm test.
There's no hash index, right?
No hashing that. Basically, look at everything covered in your homeworks 1, 2, 3, quiz 1, 2, and the corresponding materials from the lecture. Yeah.
So if we have an answer like log 6 of 20, you expect that in the form like 1 or whatever?
What do you mean? This again? I didn't get your question.
So since you said bring a calculator, do you expect all answers like is a log base 6 of 20 an acceptable answer?
Well, yes, I do expect you to calculate that because that will actually make you answer easier, because oftentimes the subsequent question may depend on the height of the tree. You don't want to carry a log 620 all over the place in your calculation. That actually adds burden to yourself. So you, for the benefit of simplifying your calculation, you might want to just calculate the number. Okay. Any other concerns, questions regarding the meter? Let me emphasize one more time. I know this year we do not ask you to turn in your homework, and I have mixed feeling about this. On one hand, this does give you flexibility to control your own schedule, to pace yourself. On the other hand, I'm not sure whether you are self-disciplined enough to kind of really do the homework, or really just when the homework solution is released, you just go and check the solution. The thing about human is that when you look at the solution, oftentimes you will kind of like, oh, this is easy, I can do it. Oftentimes you just need a little bit of hint to get it right. See what I'm saying? So, but without knowing the solution in the first place, trying to figure out kind of like being blind, that's the challenging part. So you might be surprised when you are challenged like that. You do not have any hint, you do not have a solution to refer to, and certainly the questions that are seemingly so easy now become very hard. So make sure you do your homeworks. You do your homework without looking at or checking at the solutions side by side. Okay, that's very important, and that's another reason why I'm willing to allocate enough time enough lecture time to do quiz for that reason. Which is because quiz gives you a simulation test in some sense, right? And give you even more pressure than what you will be facing from midterm and final, because midterm and final are open book and quiz is not. In other words, later on today when we carry out quiz number 2, take it seriously. Take it as if you are doing midterm and final, and grade yourself. Do grade yourself after we are done with quiz 1, go over the solution, and see how much points you get. Take this seriously. I take this as a good opportunity to kind of gauge where you are. And you still have 2 days to make up. Right? You can set up an appointment with me or the DAs to go over the things you are not sure. But I promise you the test itself, I promise you many times already, 80%, more than 80% of the tests from the midterm will be a similar type, not going to be the same, of course, but very similar type of question you have seen over and over from homework and quiz. So if you think you can solve homework and quiz problem, most of them yourself, then you shouldn't feel worried about midterm. Of course, to score the other 10, 15 points does require a little bit more kind of commitment and more in-depth understanding of the course materials, right? But even if, let's say, you throw away those, you still easily can get 80 points if you spend enough time exercising your homework and quiz. Okay? All right. Let's move on to lecture today. So we talked about extendable hashing last time. Let me just continue from where we started. Oh, it's not. Okay, so, all right, let's go from here. To give you a quick review of extendable hashing, what it does is it maintains a structure that's called directory, and then a set of local buckets. And each local bucket has precisely one page. One thing you need to remember is that for extendable hashing, there are absolutely no overflow buckets. There will be no overflow bucket at any given time. When you do, you split that. When you do, you split that, right? And for the directory, you maintain something called global depths. And then for each local bucket, you maintain something called local depths. And an invariant that holds all the time is that the local depth value of any given bucket must be less than or equal to your global depth value from the directory. Okay? And what this local depth and global depth means is the following, right? You apply a hash function over the search key value of any incoming data entry. Remember, in this particular example, 21, 19, 15, these are not the search key values themselves. These are the hash value of the corresponding search key values. Okay? I do that because I want to make sure you understand where they go, to clearly show where they go based on the hash value rather than the search key value itself. Okay? So that's so imagine I have 3 data entries. Their search key values have been hashed to 21, 19, and 15 respectively. Then with a global depth equal to 2, what I'm doing is I will look at the last 2 bits from a given hash value to decide where the corresponding search key entry will go to, which bucket it goes to. So that set 21 has 0, 1 as the last 2 bits. So we'll go to the second entry in the directory, which points to that bucket in the middle, the second bucket, right? Second bucket. So 21 goes here, and you carry out the same calculation. And 19 will end up in that very same bucket. And now you have a problem. You do not have space, and as we said earlier, extendable hashing doesn't allow you to have any overflow bucket. So what you do is you split. You split this bucket. And in this case, when you split, you basically redistribute those entries from that bucket now based on the last 2 bits of their hash values. So, which means that those with last 2 bits equal to 0, 1 stay in this bucket, and those with last 2 bits equal to 1, 1 will go to a new bucket like this. You follow me? Any question on this? Okay, cool. So we continue to 15. And let's say we continue with an example like this. Right now, every single bucket, their local depths are equal to the global depths. All of them are 2. So let's say if I insert another data entry whose search key value is hashed to the value of 20, and the last 2 bits of 20 is 0, 0, which means this data entry will go to bucket number 1, leading to an overflow of that bucket. And since we do not allow any overflow bucket to exist, we will have to do a split right away, leading to the increment of the local depth to 3, and which effectively means that you're looking at now the last 3 bits of those hash values to distinguish them. So instead of looking at only 0, 0, you look at the last 3 bits, and which means you only have 2 possible cases, which is 0, 0, 0 or 1, 0, 0. So those with 0, 0, 0 will stay in the first bucket. Those with 1, 0, 0, that's where an interesting case happens, which means you have to double, you do allocate a new bucket, right? Correspond to 1, 0, 0, but there's no way you can possibly index this bucket using the current directory, because the local depth, the global depth of the current directory is only 2. So which means you do have to increase the global depth now to 3, which effectively double the size of your global entry, because the directory effectively is using a binary encoding. By using a binary encoding, 2 bits means 4 entries, and 3 bits means 8 entries, and so on and so forth. So every time you increase the global depth, you are doubling the size of your directory. Yeah. And for those buckets you didn't split in this round, their local depth will stay at 2, which means you're going to have 2 entries per bucket to index them, because there's the discrepancy, there's the disparity between local depth and global depth for those buckets. So you have 2 entries per bucket for those ones, when the local depth is 1 bit smaller than the global depth. Okay? So that's what's going on here. And for the bucket, you have just done a split operation for, which is the first bucket, very first bucket on top. The local depth will be equal to the global depth, which is 3 in this case. In that case, you will have 1 entry per bucket for those 2 buckets. And their global depths match the local depths. Okay? So that's a quick review of what we have discussed from last lecture. Okay? So this is the insertion process. The deletion process is exactly the reverse procedure of this, which means you remove entries when necessary, and when a bucket becomes empty, you can merge that with another bucket. When all the buckets are indexed by 2 entries respectively from your global directory, that's when you know you can decrease the global depth value by 1 and cut the directory size by half. Question?
So the size of the bucket is fixed.
The size of the bucket fixed is determined by your page size. And how many data entry can fit in a bucket is determined by your page size and your size of your data entry, as well as the utilization ratio of your index. Make sense? Okay, all right. So let me move on to linear hashing. So linear hashing is designed to address this potential limitation from the extendable hashing. Based on the discussion from the extendable hashing, we immediately observe a potential behavior that's kind of that's not well. That's not gonna do well in practice if you have a skewed distribution of data entries. Okay, what I mean by that is if you have a lot of search key values that are being hashed to the same bucket all the time, which means that leads to a situation where you have one bucket keeps getting overflowed, and you are forced to split that bucket all the time. What happens is you have a single bucket or a few buckets, whose local depth values are equal to the global depth values. But for majority of your buckets, their local depth values are much more smaller than the global depth values. In other words, you increase the size of your directory by a lot, while not increasing the number of buckets accordingly. And eventually that leads to a significant overhead when the size of the directory becomes so big that this thing itself, the directory itself, outweighs the benefit of using a hash index to begin with. Okay, Victor?
So search keys don't need to be unique, right?
Well, not necessarily.
So
Search key is any attribute from your schema, so they don't have to be unique.
right.
Search key is different from key of a schema.
Okay. And so with that, what happens if we have what if we have the number of entries that fill a bucket that all have the same search key? Then anytime we split, we'll never redistribute.
That's a very good question. So let me repeat Victor's question. Victor says, if I have a lot of search key values that are essentially the same, okay, and if that leads to an overflow bucket, even if I increase, the number of bits I use to index them, no matter how many bits you look at it, no matter how hard you look at this bit, they're gonna be the same because I'm using deterministic hash function and I have same search key values coming in. The output gonna be the same, no matter how many bits you look at it. Do all of you follow his argument? So in practice, one way we address that issue is to use some particular technique called geometric perturbation. The way we do that is for when you see a lot of duplicate values in the input, and that happens to be your search key value. You add a small amount of perturbation, random perturbation, for these search key values, such that you can enforce, now you can have a strict ordering of these values, however, without affecting the order of this value against all the other values. So, see all part of it. Let me give you an example, you know exactly what I mean. So let's say you have GPH, 3.1, 3.2. And in between you have a guy who 3.15. That's okay. And you have another one which is 3.15. You know, not ideal, but fine. 2 duplicates I can handle. But imagine you have, let's say, 1,000 of this. Do you see the problem? So that's exactly the problem that Victor is talking about, right? So what I argue is you use something called geometry perturbation. What you do is you add a small random value, random perturbation. Change the state just a little bit, such that this becomes, let's say, you got my point?
Could you repeat that word? Perturbation?
Perturbation. Perturb.
Perturbation.
Say it.
Perturb.
Okay, thank you.
Permutation.
Not permutation, perturb. Change the state of something. You perturb this. Okay? Do you get the word?
Yeah, we're good. Thank you.
Okay, cool. Alright, so you add a small perturbation, and this is the perturbation I'm talking about. So it's small enough such that these values are still within the right place they are supposed to be when you compare to other values. Let me finish and answer your question. But then you can now enforce an order among these duplicate values. And when you do search, you may wonder, what happens when I do search? Okay? When you do search, you still use this value. You still use this value to look up from where they possibly are from. You still use this value to do your search. Make sense? You may wonder how you're going to do that with a hash index. How you do that with a hash index? What you would do is, so first of all, let me explain a tree index. It's much easier to explain, right? So a tree index, you remember the minimal and maximum possible value of the perturbation you have done. And then you call this search of this value become a range search of this value plus the mean perturbation value and the max perturbation value. So that's trivial. You follow me? Yes or no? And if you are using a hash index, then you do have to remember all the perturbation value you have added to distinguish the application you have. Then when you try to do hash, you simply take this value and add the perturbation one by one and hash it to look up all the value you have. You follow me? Suppose you are using alternative 2. Okay? If you are using alternative 1, this is an even simpler problem to deal with, right? Sorry, alternative 3. This is an even simpler problem to deal with. Why is that? Can someone help me with that? Why alternative 3 is much easier to deal with?
Because all the data matched with that index will be in that particular heap.
Yes, because all the records, remember these are data entries, right? These are your data entries. So all the records matching this value will be stored in a single list attached to this value. So you have a single 3.15 and many RIDs if you're using alternative 3. So the solution I propose is for the case when you're using alternative 2. Okay? Answer your question? Okay, perfect. All right, let's move on to linear hashing. So the main idea of linear hashing is to address this potential limitations with extendable hashing, which is to to kind of get rid of this expensive split operation all the time. So the main idea is that, if you compare extendable hashing and linear hashing, we can kind of think of this as two different types of personality. Okay, in the first category, in extendable hashing, this is a person who doesn't want to have anything in his or her to-do list. Whenever I have a task, I will do it right away. Okay, if I have a small problem with my whatever, I will fix it right away. I will stop what I'm doing and fix that right away. I don't like to have something hanging over my head over time. Okay, so that's extendable hashing. It's kind of like no overflow bucket at all. Linear hashing, on the other hand, says, well, if you do that, that might be too expensive, especially if you get interrupted all the time. Okay, this is okay if from time to time you have a task that you have to attend. But if you have tasks that always pop up all the time and you attend to that task all the time, and this introduces too much overhead in the system. So linear hashing says the other way. It says, okay, fine, I'm going to allow some overflow buckets to exist. Okay, that's fine, that's okay. However, I will kind of do my split in a round-robin fashion so that eventually I will come to an overflow bucket and split that. I don't split right away, but eventually the term for splitting that overflow bucket will be here, and I will be able to split that. So that's essentially the idea between linear hashing. For the construction of linear hashing, I use a family of hash functions. I denote this family of hash functions as H0, H1, H2, and so on and so forth, where I define the ith hash function as the following, which is this is what I call a base hash function. And I simply mod this with to the power n. Okay? So a base hash function, an example of this can be just hx plus b, for example. Okay? If you try to understand this one, what it does is, if you think about it, h0 equals to what? Right? That's essentially what it is. To the power 0 equals to 1. What about h1? Multiply 2 times n, right? And h2 equal to, and so on and so forth. Okay? Now we see some interesting property of this family of hash functions. This family of hash functions. What are the interesting properties? What are the interesting properties? The first and obvious property is that if you look at any two neighboring hash functions from this family, their output size differ by a factor of 2. You follow me? The output size differ by a factor of 2. N, 2n, 4n, 8n, 16n, 32, and so on and so forth. Okay? More importantly, hx mod n and hx mod 2n, for those, okay, here's the important observation, right? Pay close attention to this. For those who are being hashed to the lower half in the output, if you look at for example, if you just look at h1 and h0, right? Let's just look at h2. If you look at the behavior of h1, for those who have been hashed to the lower half in the output of h1, the output value is going to be identical to their output from h0. Okay? which means there are always half of those outputs. When you grow, when you look at H1 and H0, they're gonna stay at the same position in the output. And this is the same when you talk about H2 and H1, H3, H2, H4, H3. You follow me?
Could you repeat the last thing?
Okay. So if you look at the output of H1, the output gonna be size of 2n. I'm talking about the first half of those output. So those being hashed position 0 to roughly n minus 1. Exactly n minus 1, not roughly, right? 0 to n minus 1. That's half of the output. Those guys who have been hashed to that position by H1, if you look at their output from H0, they will be staying at exactly the same position. What about those from n to n minus 1, which is the second half of H1? Well, you kind of imagine what happens is if you try to use H0 on them, they are being wrapped around. Okay, it's kind of like you're wrapping them around in H0. But now with H1, since you're doubling the output size, you kind of cut this circle and kind of double the size. You're no longer folding it. Right? That's a way to look at it. Okay? Follow me? With that being said, so you can think of this as output of H0. This is the output of 1. This is from 0 to n minus 1. And this is 2 n minus 1. So in this case, some will be hashed here, some will be hashed here, some will be hashed here, some will be hashed here. If Hx, what happens if Hx is greater than n? Then you come around, you kind of wrapping them around. But now you cut this wrap and you kind of place them here. That's what you're doing. Okay? But for the lower half of the output, they stay exactly in the same position. Why is this important? Okay, this is important because that's the critical part about the construction of linear hashing, which I will explain next. So, if you look at the output of linear hashing, which is essentially a set of brackets, right? A set of brackets. So each of this is a bracket. Each of this is a bracket, right? You follow me? Each small rectangular box is a bucket, which means it's a page. But in linear hashing, we do allow overflow buckets to exist, meaning that potentially you will have a bucket that has many, many pages rather than a single page. Okay? And I can view, conceptually, the output of the collection of buckets in linear hashing as 3 parts. The red, the green, the blue. And the red are the buckets that you have split already. The red are the buckets you have already split in the current round. So this algorithm proceeds in rounds. So in the current round, the reds are those ones who have been splitted already. The green are those buckets yet to be split in the current round. What about the blue? Well, you're going to have the same number of blue buckets as the number of red buckets you have. With that being said, you know what they are, right? When you split a red bucket, that results in 2 buckets. The red bucket itself and 1 more bucket in the next round. That's the blue bucket. So each of the blue buckets match well against exactly 1 red bucket. Okay? Yeah,
What is splitting this bucket size?
I will come to that. Okay? But that's the high level overview. Now, the green and red buckets are indexed by the hash function of the current level. Let's say the current level is level, right? I use a level to denote that value. The current round is denoted by this value called level. The green and red buckets are indexed by this hash function h level. What about the blue buckets? What about the blue buckets? They are indexed by the hash function h level plus 1. Level plus 1. And you start with so this level thing start with 0. So initially you have h0. Okay, so the initial state of the algorithm looks like this. You have h0. And how many buckets you have here, by the way? You have exactly n buckets in this case, right? Because that's the output size of this hash function h0, right? You follow me? Okay. And initially, all these are green buckets. So you have a pointer pointing to the first bucket of the current round. The current round is level equals 0. That's the initial state of this algorithm. So all of these are green buckets. None of them have been split, right? Is that okay? Follow me? Now, when you have insertions coming in, you have entries filling up this bucket over different places. And eventually, at some point, what happens? You will have an overflow bucket, right? So imagine each of this is a data entry. This is the data. Each of the slash is a data entry. So eventually you will have some overflow buckets, right? You follow me? And the first time you have an overflow bucket, what do? In extendable hashing, you will split this bucket because you do not want to have any overflow bucket to exist, right? In linear hashing, what do? Well, you do not split this bucket. You split the next green bucket from the current round. Let me repeat this. You split the next green bucket from the current round. Okay? So my next green bucket is this one. What I will do is I will move this pointer to the next bucket, effectively making this a red bucket. While I'm doing this, you can refer back to the picture over there. So the entries here will be distributed. Some of them will stay here, some of them will come here. You follow me? So let me draw a line boundary. So we'll have one more bucket here. So let's say 3 entries here, 1 entry here. The missing part of the puzzle is how do I distribute these 4 entries, end up like a state like this, 3 entry here, 1 entry here. Well, you use H1 for that purpose. Effectively, you are doubling the size, the output size of your hash functions. You use H1 for that purpose. You use H1 for the split operation. You use H1 for the split operation. You follow me? All of you? Okay?
How does this help the overflow?
Oh, it doesn't help this overflow immediately, but eventually, as you see, it's a round robin thing. Eventually, you will have enough red buckets. You're pushing down this arrow one by one. Whenever you have overflow, eventually you will reach a state something like this. And that's the next bucket to be split. Now, anywhere if there's an overflow, you will split this bucket. And by the end of the day, when this arrow moves all the way to the end of the green bucket, what happens? You have effectively double the size of the number of buckets, and you enter the next round by moving this pointer to the beginning of the space again, and making all buckets a green color again. Okay, with that said, I don't think I have time to continue with this, so I will stop right here. And obviously, I do not have time to go over homework 3 solutions, so we'll go right to the quiz. And the quiz today is 33 minutes. And so when you wrap up, I will go over the solution really quickly. Okay, you can start whenever you get a copy of this.
post the solutions today?
Yes, I'm going over the solution today, yes. We can start whenever you get a copy of it. Yeah, you guys can try to solve this. Quiz is closed book, right? So shut up your computer, shut up your notes, and everything. Well, you can write on paper, yes. Go ahead, please. But feel free to use the laptop for calculation. If you do that. But otherwise, you can turn it off.